Hi, I'm Max Hopkins. I'll be talking about hypercontractivity and symmetrization on high-dimensional expanders. Okay, I want to start with some basic background, both on HDX, but even on basic Boolean function analysis, which maybe some of you are not familiar with. So I want to start with hopefully a fairly unobjectionable claim. The study of Boolean functions, right, functions f on the cube to 0, 1, are a fundamental study in theoretical computer science. We model many objects in computer science as Boolean functions, and one of our core interests is in analyzing the behavior of these functions. Boolean function analysis is the study of such functions f via their Fourier decomposition or other analytical means. This is the decomposition of f into its monomial basis, right? In other words, every f has a unique decomposition into the sum f hat s chi s. This is just in the monomial basis, where each chi s is just this parity function over the subset of coordinates in S. Okay, the critical insight in Boolean function analysis usually revolves around controlling the behavior of f's low-degree components. In other words, for any given fixed I, we define f less than or equal to I to be the projection of f, just the sum over components up to size I. This is essentially the low-degree polynomial part of f. Usually this corresponds to sort of the poorly behaving fraction, and we'd like to prove that f has sort of low projection onto this or something along these lines. The king of low-degree analysis, and this was sort of brought into modern light by Kahn-Kalai and Lineal, is what's called the 2 to q hypercontractive inequality. Or in this form, the Bonami lemma was proved by Bonami in 1970. It says for all q greater than or equal to 2, the q norm of the low-degree component of f is at most root q to the I, roughly, times the 2 norm of f. And basically, if you haven't seen this before, what it says is that low-degree polynomials, or the low-degree components of a Boolean function, are smooth. They aren't too spiky, right? Because a function that is spiky will have, when I take a q's power, it'll sort of blow up these spikes. And this is saying that the difference between the q norm and the 2 norm is not all that much. So this must be a smooth function. Okay, hypercontractivity is an extremely useful inequality, a paradigm. It's central to things like the KKL theorem and Frege's-Hunte theorem. They're used in social choice, in PCPs, and hardness of approximation. It's used in SDP inequality gaps, also in concentration of measure, the entropy method, log-Sobolev inequalities, also that analysis of Markov chains. It's used all over theoretical computer science. It's an extremely powerful inequality. On the other hand, it turns out that sometimes, despite the hypercube being such a natural domain, in some problems we are actually interested in functions on domains beyond the hypercube. For instance, product spaces, subspaces, or something like this. And indeed, it turns out that several recent breakthroughs have been unlocked by moving to a theory of analysis for functions on domains beyond the cube. Right? Very early on, a theory on products, the p-bias cube, led to the famous sharp threshold theorem of Frege and Bourgain. More recently, there was a big advance in number theory, something called the Furstenberg-Sarkozy theorem, using hypercontractivity on products, which is very interesting. We've also seen lots of advances in hardness of approximation, PCPs, the 2-to-2 games conjecture, PCPs with optimal alphabet soundness trade-off that come from hypercontractivity on the Grossman and other extended domain. So this has been a very powerful tool in the last 5 to 10 years. For the purposes of this talk, we're just going to focus on a very special case, essentially the simplest case beyond the cube, which is the domain n to the d. Right? If n is 2, this is just the cube, but we'll think of n as being quite large in this case. So how does hypercontractivity work on the domain n to the d? Well, this turns out to be much harder than the cube. In fact, it took like 30 or 40 years to resolve a tight hypercontractive inequality here. And the reason for this is that hypercontractivity is actually just not true on this domain. In particular, there are low-degree local functions, for example, dictators, juntas, this sort of object, where hypercontractivity fails. And this is very easy to see. You can just directly compute, for instance, for the function, the indicator of the first coordinate being 5 has 4 norm 1 over n to the 1/4, which is much larger than 1 over square root n, which is its 2 norm. Right? So this is not a hypercontractive behavior. In the last 10, 20 years have seen the development of a theory of what's called global hypercontractivity, which essentially proves that these are the only bad examples. That any function that is global, or not correlated with one of these local examples, is hypercontractive. And so the goal here is to prove, in all of these domains, except, I guess, the short code, what's called global hypercontractivity. Okay, so if we've already proved, this sort of bound on n to the d, what's left to do here? Well, in application, a major barrier in using entity and also these other extended domains is its density or size. Let's look at, say, a base example. Parallel repetition is a classic paradigm where you take a weakly hard problem and you repeat it d times. This is essentially using sort of analysis over n to the d. The problem with this type of hardness amplification approach is that it massively blows up the size of the instance you're working with. If you start with a problem on, sort of n variables, you'll end up with n to the d once I embed into n to the d. And if d is large, this is going to blow up to superpolynomial size, and we're not going to be able to use this object. So somehow in many applications, the fact that these domains are so dense is a major barrier. And this raises sort of I think, a natural question. What is the main focus of this talk? Can we find sparse domains, in particular just in the restricted setting, sparse subsets of n to the d that are hypercontractive, or more accurately, that are globally hypercontractive? Okay, so it turns out that a natural candidate for this problem are a class of objects called high-dimensional expanders. These also have the benefit of being very closely related to parallel repetition and sparse PCPs, the unique games conjecture, and the proof of the 2-to-2 games conjecture, and SDP integrality gaps as well. So these are somehow objects that are very closely tied with many applications of hypercontractivity. And roughly speaking, you should think of these as very strongly pseudorandom subsets of n to the d. In which case, you might hope, if these are sort of sparse models for n to the d, that they might maintain a theory of analysis and hypercontractivity. So let me now actually sort of define for you what a high-dimensional expander is, and hopefully you'll get some intuition for why we might think a theory of analysis would hold on these objects. So I want to give essentially a distributional view of expander graphs and high-dimensional expanders. So let's say that we have a bipartite graph G. Right? This is a graph on two balanced sides of n vertices and a set of edges going between the two sides. We can always view this graph as a two-dimensional distribution, x1, x2, on n squared, right? Just by drawing a random edge, I generate a pair, a, b of numbers in n squared, and this gives me some distribution. A graph G is called a lambda expander. Basically, if this two-dimensional distribution, these variables x1 and x2, act approximately independent, right? If this graph is sparse, these variables might be extremely correlated, and this sort of incredible property of expansion says there are sparse graphs, very sparsely supported distributions, where nevertheless the variables act independent in the sense that for any functions f and g, the joint expectation of f times g across this product is roughly the product of the expectations. It is roughly expectation of f times expectation of g up to some additive error in the expansion parameter lambda. Okay, so you can see this is sort of the two-dimensional version. High-dimensional expanders just generalize this idea to d dimensions. Right, so a hypergraph that's a d-dimensional subset of n to the d, x1 through xd, is called a lambda high-dimensional expander. It's called a local spectral expander. If first, all of the two wise marginals xi, xj are approximately independent, i.e. they're lambda expanders. And two, critically, this holds even under conditioning on the value of any of the remaining variables, right? So if I take xi, xj, and I fix the value of all the other variables in the distribution to something that's in the support, even conditioned on these values, xi and xj should remain approximately independent. That is the notion of a high-dimensional expander. This, I'll say, formally is technically first defined in Gerlach, Schütz, and Liu. They call this a lambda product. But it's basically the same notion as a local spectral expander that sort of historically is from Kaufman, Kasch, and Lubatsky and Oppenheim. Okay, so it turns out that we actually have very, very sparse constructions of high-dimensional expanders. This is sort of a miraculous early work of Lubatsky, Samuels, and Vishne, extending classical Ramanujan graphs, who prove that for all lambda greater than 0, there exist families of lambda high-dimensional expanders of size about n times lambda to the d squared. Right? So in particular, this is what's called bounded degree. For every fixed vertex, there's only some function of dimension, many hyperedges touching that vertex. I want to briefly point out that this is much denser than sort of classical pseudorandom objects you might be used to, like extractors, samplers, walks on expanders, this sort of thing, which have degree more like n times 2 to the O of d. So here we're paying for this additional pseudorandomness in the d squared in the exponent. But as a result, these objects are sort of by definition behaving better under restriction. And this is really the critical insight in showing that these objects satisfy a theory of Fourier analysis, as we'll talk about in a minute. Okay, so let's actually talk about Fourier analysis and hypercontractivity on these objects, these notions of high-dimensional expanders. So first, let's take a little bit of a step back and recall how general Fourier analysis works on product spaces on n to the d. So I'm not going to go into exact details here, but roughly I'll claim that any function f mapping n to the d to r has an analogous version of the Fourier decomposition called the F-Ron-Stein decomposition, which just breaks f into components coming from each subset. F equals s x, this is the F-Ron-Stein components, and roughly speaking, f equals s is the contribution to the function coming from coordinates s. You basically just project onto these coordinates and then use inclusion and exclusion to subtract off contributions coming from subsets of the coordinates. Nothing complicated. Again, as for the cube, usually in application, we're interested in bounding the behavior of low-degree components. So we'll define the same f less than or equal to I as the sum of the components up to size I, the low-degree components. And only quite recently, Kivash, Lifshitz, and Marcus proved an optimal hypercontractive theorem for n to the d. They showed that for all q greater than or equal to 2, and global, a function that is not correlated with any local subset, f, the q norm of the low degree component is at most q over log q to the I times the 2 norm of f. This is like a slightly strange term. If you remember in the Bonami lemma, this was root q, but it turns out that this is tight. In fact, before we had sort of polynomial bounds on this, and they were the first to really get to this linear q over log q regime. And I won't go deeply into this, but this is roughly because plus minus 1 to the d, the cube acts Gaussian, while n to the d for large n acts Poisson. And this is sort of the dependence you would expect for a Poisson random variable. Okay, so this is sort of the answer on n to the d. What can we say about high-dimensional expanders? Well, in 2022, in independent work, Ger, Lifshitz, and Liu, and Boffna, Hopkins, Kaufman, and Lovett established sort of a preliminary set of hypercontractive inequalities for q equals 4, for the 2 to 4 norm. First, let's look at the results of Ger, Lifshitz, and Liu. They proved that for a certain type of high-dimensional expanders, which have sparsity roughly n times 2 to the O of k cubed, so a very, very sparse object. They proved for all global functions that the 4 norm of the low degree component is at most I to the I times some function of the 2 norm and an L infinity norm of f. There are sort of two things here that you probably notice right away are different from traditional Bonami. One is this infinity norm dependence, and one is I to the O of I instead of 2 to the I. And I'll just note that really the one that neither of these are, of course, what we would want. The one that really matters is this I to the O of I. That it turns out in application, achieving sort of truly singly exponential dependence on degree is critical. I won't go deeply into this, but roughly the reason for this is that when you apply noise, you need the eigenvalues of the noise operator to cancel this coefficient coming from hypercontractivity. And the eigenvalues only cancel correctly if you manage to get this 2 to the O of I dependence. So this is a very, very critical dependence to achieve in application. The second independent work with Boffna, Kaufman, and Lovett, we showed that there exist subsets, also based on a stronger notion of high-dimensional expanders, of size n times 2 to the 2 to the k, such that you do achieve this correct dependence, that for all global functions, the 4 norm is at most 2 to the O of I times some function of the 2 and infinity. And again, this still has this L infinity issue, but roughly speaking, you get the right dependence, and this allows you to prove operator hypercontractivity and sort of these applications you need 2 to the O of I for. But on the other hand, this is often sort of too dense, right? We pay, to get this right dependence, we've paid exponentially in the size of the object. I can't take k to be even greater than, say, log n here and still end up with a sparse object. And since often in application, the larger I can take k, the better strength of my result is going to be, like in soundness amplification in PCPs or distance amplification in codes. This all depends on setting k to be large. This is really too dense of an object to use in application. So somehow, GLL managed to get these much sparser complexes, but the wrong coefficient, and BHKL got much denser complexes, but the right coefficient. So it's a natural question, can we achieve the best of both worlds here? And also, can this be extended beyond 2 to 4? In some applications, you really need a large Q. You take Q somehow to be scaling with the function density. So even super constant Q is necessary. And can you get rid of this L infinity independence, which doesn't appear in traditional versions of the theorem? So this brings us to our first main result, which is a near optimal hypercontractive inequality for high-dimensional expanders. Particularly, we proved that for any sufficiently strong part-tight high-dimensional expander, this definition that we covered a couple slides ago, then for all q greater than or equal to 2, and any global function, the q norm of the low-degree component is at most q to the I times f of 2. So this is off only by this log factor from this optimal hypercontractive bound of Kivash, Lifshitz, and Marcus. So it's very close to optimal, to extending that bound. And moreover, it holds for similar size subsets to Gur, Lifshitz, and Lu. In fact, slightly better, it holds for things of size n times 2 to the O of d cubed. This should have been d cubed, not k cubed. Sorry. And I'll just say that this work didn't come out of nowhere. This was all built on the foundations of an initial basic theory of Fourier analysis, understanding Efron-Stein components and similar bases of Dikschain, Filmus, and Harsha, and also in joint works with Bafna, Kaufman, and Levitt, and Gatande, Kaufman, Levitt, and Sheng. Okay, so I want to spend a little bit more time talking about how one actually goes about proving an optimal hypercontractive inequality, which in fact is really just a corollary of what I think is the actual main contribution of this work, the main result of this work, which is an extension of what's called Bourgain's symmetrization theorem. It's a very powerful method in analysis. So how are we going to prove not just hypercontractivity, but any sort of analysis theorem we're interested in looking at on product spaces? The core issue is really that the Efron-Stein components don't act as well as the Fourier basis. We don't have access to a lot of tools that we're used to being able to use on the cube. So the core idea that was sort of pioneered by Kahan and Bourgain is to try to symmetrize the function in some way that allows us to reduce to analysis on the cube. What do I mean by this? Well, in particular, given a function f on n to the d, Kahan and Bourgain defined its symmetrization to be a function f tilde on n to the d Cartesian product with plus minus 1 to the d, which basically just hits every Efron-Stein component with a corresponding character of this Boolean string r. Right? So you have the sum over subsets s of f equals s times the parity function of ri on these coordinates. In other words, if I think of fixing any x, this symmetrization is the unique function whose Fourier coefficients are the Efron-Stein components of the original function. The idea here is that if we can show that f and f tilde are related to each other, say they were similarly distributed or something like this, then we can analyze the Efron-Stein components by actually doing standard Boolean function analysis on the cube on this symmetrized function for fixed x. And indeed, this is what Bourgain proved. Bourgain proved that if you're only interested in q norms, that the qth moment of f is similar to the qth moment of the symmetrization of f up to the addition of a little bit of noise, in particular where this is the classical noise operator, t rho f multiplies each Efron-Stein component by rho to the x. So formally, Bourgain proved what's called the symmetrization theorem, which says for any f mapping n to the d to r and q greater than 1, the q norm of f is sandwiched between the symmetrization of f with a little bit of noise applied on either side. CQ is just some constant depending on q that I won't write out explicitly. Our main result is an extension of Bourgain's theorem to general part-tight high-dimensional expanders. Right? So in particular, a product is a zero HDX. It's a perfect expander. So this theorem strictly generalizes Bourgain's result. It says for any part-tight lambda HDX, then the symmetrization theorem holds with the 1 minus little o of one term and 1 plus little o of one term on the sandwiching sides. And there's some dependence on dimension here, such that you need to take lambda to be something like inverse exponential in dimension, which is why you get this 2 to the d cubed type result. Okay, so I won't go deeply into how you prove hypercontractivity once you have the symmetrization theorem, but the idea is quite simple. It's due to O'Donnell and Zhao, and you basically just pass to the symmetrization and then apply standard hypercontractivity. That's and then you massage things a little bit, but that's roughly the idea of all these types of analytic inequalities. Apply symmetrization and then apply on the inside components the standard Boolean function analysis result, and this will sort of get you what you want. Okay, so I want to spend the last 5 minutes or so giving a rough proof sketch of the symmetrization theorem. So I'm going to start with n to the d, and then I'm going to give sort of a high-level idea of what are the barriers and how do you extend this theorem to high-dimensional expanders. Okay, so our goal, which we'll rephrase slightly by moving the noise operator from the right side to the left side, let's just prove the upper bound. We want to show that the q norm of t1/2 f is upper bounded by the q norm of the symmetrization of f. So there's sort of two steps to this process. First, at the start, we're going to do sort of a reduction to one dimension. This is a very classical technique. It's how you would prove the standard operator hypercontractivity theorem as well. We're basically going to assume that we have a one-dimensional version of the inequality. This is easy to prove directly. We're not going to worry about this. And we'll show how to reduce the d-dimensional version to this one-dimensional version. Okay, how we're going to do this, we'll sort of do this in two steps. The first step is what I'll call decorrelation, which is basically to write this global operator t of rho or t of half and symmetrization as sort of a coordinate-wise product, a product of coordinate-wise operators acting on each coordinate of n to the d independently. In other words, we'll define these coordinate-wise noise operators for any rho, for any real-valued rho. We'll define t rho I of f to just multiply the Efron sign components that contain S by rho and leave all of the other Efron sign components unchanged. Okay, so because the Efron sign components are eigenvectors of this operator, it's very easy to verify that T rho of F, which I recall as this sum of rho to the S F equals S, is exactly the product of these Ti operators, right? T1 rho through Td rho applied to F. And maybe slightly less obviously, we can actually also express the symmetrization of F in this form, that the symmetrization of F at XR, which is this sum of product of Ri times F equals S, is exactly the application of T1R1 through TRDD to F. So you can write both of these as a product of coordinate-wise noise operators. So we've reduced the problem to showing that the Q norm of T rho 1 through D applied to F is at most the Q norm of TR1 through RD, where these are random, random binary values applied to F. And this, if you've studied Boolean analysis before, should scream at you the replacement method, right? What we should do is sort of one by one walk through these coordinates, treat each of them as a one-dimensional problem, and use the one-dimensional symmetrization to switch from T rho 1 to TR11, and just repeat this process. And indeed, this works. It's a very elegant proof. I think originally by Bourgain, but I'm following the exposition of O'Donnell and Ball. So the second step is exactly this sort of replacement method via what I'll call localization. So like I said, the idea is to replace each of these Ti 1/2 one at a time. Okay, so maybe these should have said 1/2. So we'll start with this expectation. This is the qth moment, the expectation of T1 half through Td applied to F. And we'll do a very basic first step. We'll localize by saying, first I'm going to draw x2 through xd, and then sort of conditioned on x2 through xd, I'll draw x1. On a product, you don't have to really condition, right? There's things are independent, so it doesn't matter what x2 through xd are to an extent. But if you move to high-dimensional expanders, things aren't independent, and you have to be careful about condition. Regardless, draw x2 through xd first, then have an inner expectation over x1. The point is now that if we view x2 through xd as fixed, we can really view this inner expectation as a function of one variable. In particular, we can localize the operator, this noise operator in the first coordinate, just becomes the one-dimensional standard noise operator applied to this one-dimensional function where I've fixed the values of x2 through xd. Right? So this inner function becomes a one-dimensional function of x1, and we're just applying the standard one-dimensional noise operator. And that means that I can apply the one-dimensional symmetrization theorem. Right? So this will get me to, again, this outer expectation on x2 through xd of the inner expectation now over r1 and x1, because I've applied the symmetrization theorem. And now I can pull these back to the global expectation. I can sort of delocalize, and I end up with the expectation over t r1, and then the remaining is t half f. And now I can complete the proof by just doing this process, repeating this process for t2 through td. Maybe I have to sort of permute the ti's to show up in front first, but it doesn't really matter. This method will work for repeating on the rest of the variables, and that'll prove the inequality that we want. Okay, so that's sort of the general idea on n to the d. How do we extend this to high-dimensional expanders, or what goes wrong? There are really two main barriers to this method, right? I said that there are sort of two steps. There's this decorrelation step where we split T rho into coordinate parts, and then there's a localization step. And the problem is that neither of these steps works. So in particular, because of lack of independence, coordinate-wise decorrelation fails, at least naively. It's no longer true that T rho of f is equal to the product of these coordinate-wise operators applied to f, nor is the product of the T Ri operators equal to the symmetrization of f. And second, localization also fails, or at least it probably fails. It's not clear why this would be true. I guess I maybe don't have a counterexample, but I expect that this is not true, that if you look at the coordinate-wise operator T1 applied to the global d-dimensional function g, then this is not equivalent to applying T1 half to the restricted one-dimensional version of this function g. Right before in the previous slide, g was really like T2 through TD applied to f, but generically you would want this sort of localization to work. So neither of these steps works, and there are sort of two key ideas to get around this fact. The first is that even though you want to define the noise operator in sort of this analytic extension way that I did, where I multiplied each component by Ri, since this is what allows you to express symmetrization as an application of the noise operator, it turns out at the coordinate-wise level, the right idea is to define these in terms of projection operators rather than defining them in terms of their action on the Efron-Stein components. So I'll define the ith coordinate operator as basically being Ri times the identity minus 1 minus Ri times the projection operator, where EI basically just re-randomizes the ith value of f, the ith value of x on f. And roughly speaking, the idea is that as projection operators, we're already looking at conditional expectations, and when I localize, what I'm looking at is also a conditional expectation. So these sort of localize correctly, unlike the coordinate-wise versions in Efron-Stein. And this means that when I product them and compose them, that all of these T rho I also localize correctly as well. So this sort of fixes this second issue. To address the first, the idea is to prove that while this doesn't hold generally, there is some Q-norm approximate version of decorrelation that works on general lambda high-dimensional expanders. In particular, we prove the operator Q-norm, the difference between T rho and the product of the coordinate-wise operators, is at most about lambda to the 2 over Q. So if I take lambda quite small, then the difference between these in Q-norm is essentially negligible. This is just going to show up as this little of one error term that was in the symmetrization theorem. And the key idea here is actually just a simple application of what's called Ries-Thoren interpolation. Basically, the idea is that because I know that all of the local 2 norms are bounded, right? This is really what this sort of local spectral expansion said. I can use interpolation to argue that the Q norm local correlations are also bounded. And then I can use a variant of sort of what's called the local to global machinery to use these bounded local correlations to prove bounded global correlation of T rho and its coordinate-wise operators. I won't go too deeply through this. This is really sort of following the general high-dimensional expansion or local to global method. So somehow really the new insight here is that high-dimensional expanders are generically Q-norm bounded locally, and that if we define our projectors in an operator sense, everything localizes well in a coordinate-wise sense as well. So this allows us to apply the replacement method, which is a much, much cleaner method of proving hypercontractivity than was used in Gerlach-Lifshitz-Liu or in our previous work with Bafna, Kaufman, and Lovett, and allows us, not only to get near optimal dependence on Q, but to remove the infinity norm and these various improvements. Okay, let me end with just a few open questions. My first question is, this method that I've given you so far is fairly specific to n to the d. There's no version of the symmetrization theorem that's known for Grossman or Lie groups, but it would be incredibly nice if this held. The proofs of these results are unfortunately quite complicated. The Grossman was simplified somewhat in recent work, but it's still a fairly complicated algebraic proof, and it doesn't seem to extend all that well to objects like tensors or pseudorandom subsets that we want in applications like towards the unique games conjecture. So if you could somehow prove a version of symmetrization on these other extended objects, it might be a very powerful tool, and I would really like to see this. Second, having some trouble going here. I mentioned briefly earlier that our methods actually require quite strong expansion of the complex. You need to take the lambda spectral expansion parameter to be like something like 2 to the minus d, inverse exponential in d, whereas many natural objects really only satisfy about lambdas like 1 over d. And much less than hypercontractivity, we actually don't even know a theory of basic Fourier analysis on these. We don't know a Fourier basis or whether something should exist. So there's a lot open here in this sort of regime of weak high-dimensional expansion. Another natural question is whether we can prove lower bounds on the size of x, subsets of n to the d that are hypercontractive. Even if you manage to improve the above, this would still give subsets, that are n times 2 to the o of d squared, rather than n times 2 to the O of d, like traditional pseudorandom subsets. And I wonder if this might actually be tight. And is there a way to prove a lower bound that n times 2 to the omega d squared size is actually necessary for global hypercontraction? There's some intuition for why this would be true based on needing good structure and sort of all restrictions, which requires more density than a standard pseudorandom object would be, but I don't really have any idea how one would prove this. And finally, probably the most important question is, can we actually use these gadgets and this theory of global hypercontractivity for something? I mean, the theory has been incredibly useful on general product spaces and Lagrange and these extended domains, but it's not yet clear quite how you would plug a high-dimensional expander into these contexts and make an improvement. It's related to these ideas in 2-to-2 games, SDP gaps, this breakthrough work, current best paper in this conference on quasi-linear PCPs, but it's not clear how you would directly apply this theory of global hypercontractivity to make progress on any of these problems. So it would be extremely interesting if you could find some sort of classic application area for these sparse hypercontractive inequalities.